Hello, I'm Dr. Sam Stevenson. I am your instructor for Chemistry 111 and 112, the online version. Mr. Ken Berry is also an instructor at Marion Military Institute in chemistry. Your course administrator is Miss Carol Hughes. You'll find Carol very amenable, and she's very, very helpful with regards to your standing in the course and labs, especially labs. She and Mr. Berry are running the lab part of this course, and I'm just delivering an online lecture series for both semesters, Chem 111 and 112. We'll talk about a little bit about rules for success in the fall and spring semesters. They're no different. I'll show you some historical data for Chem 111 and 112 from last year, so you can get some idea of how this course evolves. Review from Chem 111 syllabus. We'll talk a little bit about that as well when it's posted. Chem 1 Chapter 1 discussion. And so let's talk about the rules for discussion, or the rules for success in this course. This is your freshman year in college. It is not grade 13. Just because you opted to go to an academy, and 95% of you in this class are in the SAP program. Anyway, just because you're in this is your freshman year in college, guys. This is not high school. This is not grade 13. So take all your bad habits that you used in high school for last minute and throw them out the window. You're going to need to be very successful, and you will need to employ some good time management skills. And so your time management skills are key to your success in this course and at the Institute. Again, walk away from your bad habits of waiting to the last minute to complete an assignment. 90% of you do this. Don't do it here. It will not work. You must keep up the assigned work as prescribed in the syllabus, and the syllabus will detail day by day what your reading responsibilities are, what your mastering chemistry responsibilities are. Mastering chemistry, by the way, is where you do your online homework. Regardless of your high school chemistry course, this is much, much deeper in content, breadth, and scope. So do not come into this course with the idea that, oh, I've had AP chemistry, so I'm equivalent to college. Nothing further could be from the truth. AP chemistry is, in my opinion, a farce. It's nowhere close to college chemistry, from what I have seen in the standardized exams for chemistry. So first, do all the assigned homework the day it is assigned in the syllabus. Do not get behind. This is a very fast-paced course. It's deep in content, deep in conceptual framework. So keep up with the reading. Do not get behind. With regards to the reading, I would recommend read. It's just 3 or 4 pages a day. And so read each page in the assignment for that day and take notes. Look at each paragraph, read the paragraph, ask yourself, what did this person say? What did the author say in this paragraph? And write it down in your notes, in your reading notes. Your reading notes you'll be able to use during various quizzes that we have in the course. And so you want to make sure that you have reading notes when you go into the course. If you don't have any reading notes, you won't have any resources during the types of quizzes that we'll give you along the way. So do not wait until the last minute. You'll drown in the concepts. Again, this is a conceptual course. You must understand the concepts to be successful in this course. This is a deeply, deeply conceptual course, much deeper than you've ever been before. Mastering Chemistry is online. It's the conceptual homework. There's some math. It's about an 80-20 mixture of critical thinking and quantitative reasoning, where the quantitative reasoning is the math part. I'll usually require about 5 to 6 hours per chapter in this course. Work on it daily. You don't eat once a week. You don't do this course 1 day a week. Do not procrastinate. Especially do not wait until the last hours of the course or the deadlines, I should say, to complete assignments. This course will drown you if you do that. Of course, the course websites, of course, are Moodle, where the course is posted. All the lectures and videos, so on and so forth, are posted on the LMS Moodle. Mastering Chemistry will be posted on Moodle. PowerPoint, my PowerPoint lectures and videos will be posted on Moodle. Also, if and when you get your access to Mastering Chemistry through the requirements of this course, go to their section where you can practice quizzes. That'll be a lot of help, and they're mostly conceptual. They're not usually deep in math. Also, check your email announcements regularly. I will not chase you. You must stay up with me, and any comments that I might have regarding this course will be made on email. So if I make a change in the syllabus or something occurs where we have to change our trajectory, that'll be in your email. I will also be accessible regularly on Zoom sessions. So attend all Zoom sessions when they're offered. During the Zoom sessions, I'm not going to do a lot of lecture because that's what you're going to get in these slides. But what I will do is help you with concepts. And so I'm not going to do your homework for you. I'll help you along the way with the concepts. But the big idea here is that the Zoom, at least once weekly on Friday afternoons, is where you'll be able to interact with me face to face. Another rule for success would be to develop small study groups, 2 to 3. Anything more than 3 becomes a gab session, and you guys are seen it thousands of times. So keep it small, keep it simple, and make sure that the people that you are hanging with, that you're buddies with or whatever, make sure that they have common goals that you have. And so your study groups in that regard will be far more effective. If you have somebody in your study group who doesn't share your goals, you may find some problem there. Use the chemistry laboratory for studying. My 13 years at Marion, I had the labs open every afternoon and every evening until lockdown at 10 o'clock or whatever it is. At which time the guard will come by and lock the chemistry building up. But you have access to the chemistry lecture hall and the laboratory, the north end of the laboratory, and which has 6 computers in it. So you guys have access to a quiet place. It's a sanctuary for studying. So you take advantage of that. Also take advantage of the Academic Success Center. You will have peer tutors in the course, and they will be working with you at the Academic Success Center for help and tutoring, and elaborating on concepts in the course, and maybe they'll help you out with some of the math when it's a consideration for you. So let's look a little bit about last year's success. Course attrition is 20%. That means if I have, and there's more people than this in the course, but if I have 100 starting at day 1, then I will have 80 people taking the final exam in May. That's attrition, so it's 20%. It's below the norm for college chemistry, believe it or not, which is usually 30 to 35%. The reason the course attrition is lower is because we give you a great deal of access to resources, including your instructors, including tutors, including the Academic Success Center, so on and so forth. And so our course attrition is much lower than it is nationally for the first year of college general chemistry, which is about 30 to 35%. Last year's fall grades, you can see the distribution, 15% A's, 25% B's, so that's 40% overall. The remaining 60% were C's, D's, and F's. Don't get caught in that curve. If you're serious about your objectives and your plans, you want to be in that top 40%. This course is a mainstream college general chemistry course. It is not a high school prep course. It is college general chemistry. It's the same course you would take at any college or university anywhere in the United States that has an accredited course in chemistry. In terms of semester hours, credits, you have 4 semester hours, 3 for lecture, 1. Looking at last year's performance, we do a pre-test and a post-test. The pre-test is shown to you in the gray area. Okay, you guys, this is the Gaussian distribution that we talked about, or that we will talk about. You guys have all had AP chemistry, but if you look at this data in the gray area, you guys, as a rule, over the last 10, 13 years, have all fallen well below the 10th percentile. Last year's class was at the 4th percentile on the pretest. The same exact test in May is the blue area. And so in May, you have all these big scores, and these are called percentile scores. The exam has 60 questions in it, and the national mean on this course is 35, which means the 51st percentile. It's a little bit above the 50s. So a Gaussian curve, bell-shaped curve. And the percentile for this course is, last semester was the 64th percentile for the mean. So as a mean distribution for the course last semester, this course that you're taking right now with myself and with Mr. Berry, you will exceed the national norms. I'm sure of it. And so with that said, you are taking a college general chemistry course, one of which is you could look at it as your academy chemistry course, because you could, if you get an A or a B in this class, you can easily test out of chemistry when you hit the academy or subsequent colleges. The syllabus is posted on Moodle on the admin tab, and I'll cover that more deeply and more thoroughly at another time. I'll introduce myself. I'm Sam Stevenson. My PhD is at University of South Carolina. I'm a Vietnam War veteran. I was drafted for the Vietnam War in '71. I served in the 7th Fleet. My duties over the years, I stayed in the Navy for a while, active and active reserves. My duties were largely at the Naval Regional Medical Centers in Yokosuka, Japan, and California. I was also attached to the 7th Fleet Seabees for a while. I have a Bachelor's of Science in Chemistry from Northern Arizona University and a PhD from University of South Carolina. I'm an organic chemist, and that means that I was deeply involved in the natural product synthesis and organotransition metal synthetic methodologies, which probably mean nothing to you at this point. I have a background of 18 years of research in industry as a research scientist, areas where polymer synthesis, a technique that we use for looking at large molecules is called NMR, or nuclear magnetic resonance spectroscopy. And we looked at, one of my postdocs was looking at the three-dimensional structure of a very large enzyme molecule as it affected as a growth hormone in bovine. I also did a postdoc in carbohydrate enzymology while in Europe. I have 21 plus years of teaching experience in the graduate and undergraduate courses in chemistry, and the course you're taking now is my course. I took 13 years for an undergraduate general chemistry course and put this thing together, so this is what you're about to embark upon. I was also the technical editor of your textbook. The 11th edition During the 10th edition, which I was using, I kept calling them up at Pearson. This is wrong, that's wrong, change this, change that. And so they asked me if I would edit the 11th edition of the textbook for technical errors and further clarity, and I did that. But my most profound accomplishment while at Marian was that I have sent more than 1,300 of you guys to the U.S. military academies in 13 years. And so that's where your success is. Let's look at Chapter 1. We're going to talk about matter, its properties, and measurement. As in course in chemistry or any other course in sciences, you're going to have a lot of definitions, a lot of nomenclature to be lucid in conversation and understanding with that course. Well, this course is no different. Chemistry is all about matter and how it interacts with itself. And so we'll begin our discussion talking about the scientific method, and then properties of matter, classification of matter. We'll talk about measurement units that we use, called the SI system, which is coupled with the metric system. We'll talk about density largely, a little bit about percent composition. Uncertainties in measurement. There's a lot of uncertainties in scientific measurement. You need to know what they are. Random or systematic. And we'll talk a little bit about sig figs. I don't personally get hung up on sig figs, but just because your calculator gives you 10 figures for an answer, you haven't set your calculator appropriately. You need to use significant figures to report your data in reports that you're going to submit during the course. So sig figs are not a real big deal, but don't be stupid when we come to them. Louis Pasteur lived in the early to late 1800s. He was a French chemist. He was trained as a chemist. He developed germ theory. So he went from chemistry to microbiology. And microbiology was in its infancy in that day because there were a lot of limitations on microscopy and what the scientists of the day could actually view in biological specimens. So he developed this germ theory. Germ theory was totally different as a hypothesis for the day. He identified and figured out that these unseen microbes, be they viruses or bacteria, are the critical component for ailments, and so he developed germ theory. He also understood that if you, looking at dairy products especially, spoilage of dairy products was a big problem in the day when he was alive and doing his work. And so he developed a process called pasteurization, named after him, of course, where the microbes are alive and active at temperatures below 100 degrees C. He would take, say, milk, for instance, and boil it, and then seal the container once it was boiled after 10, 20 minutes, whatever he used. And he basically had a sterilized sample, dairy sample. And so that's the pasteurization is what the current, nobody's improved on it. Pasteurization for all your dairy products, milk, cheese, yogurt, so on and so forth, occurs before, at some level, in most cases, for consumer products. Also, rabies was a big problem in the day. People would get bitten by wild animals in the forest, and rabies were a concern. He identified the microbes that were responsible for rabies, isolated them, and then neutralized them. How did he neutralize them? He pasteurized the system. He brought it to a boil, and then here's the genius of it. He inoculated patients or people with the dead virus with the theory that the immune system would attack the dead virus and build up its own immunoresponse relative to that virus microbe. And in this case, it was the rabies microbial system. And so he identified a cure for rabies. And so he not only went into germ therapy and pasteurization, but he went yet a step further as a physician, basically, in vaccination. And he is called the greatest physician of all time by some folks. Certainly, I think he is up there with it. He was a chemist by training and profession, but that didn't. There were no silos for this guy. Louis Pasteur went on to make many developments and advances in science, and particularly in microbiology. So, hypothesis and theory. Here's the idea. Okay, so let's say you make an observation right here. Start on the left. And so you make an observation, natural or experimental, and you develop a hypothesis that explains that observation. Then you give the hypothesis is a tentative explanation of your observations. And so you develop a series of experiments that are designed to test the hypothesis. And most hypotheses are not full and complete in their origin. And so you'll have to revise your hypothesis as with increasing experimental data. You cannot cherry pick the data you like. All the data must fit for a hypothesis to be truly become a standard or a theory. So you have to revise your hypothesis based on experimental evidence. So this is an iterative process of development and explanation and evaluation. Finally, when your hypothesis fits with all the data that's available, you then develop what becomes a theory or a model. And the beautiful thing about theories is it allows you to predict outcomes. And this is the beauty of the scientific method. So you have an observation, you develop hypothesis, you go through this iterative process, and you identify a theory that amplifies the hypothesis to be able to give predictions. And then experiments, not only you, but your colleagues in the sciences are all involved in the theory. And so they're testing the theory, as we'll talk about the atomic theory, the current theory of atomic theory. And anyway, so the scientific community around the world does experiments to test the predictions of theories. And where the data doesn't fit, again, you cannot cherry pick your data. All the data has to fit. You may need to modify your theory. And we are set right now in a whole bunch of politically charged theories like climate change versus global warming, the mankind endeavor, so on and so forth. So there's a lot of theories. People tend to take theories and hold a lot of emotions with them over the years, as I've seen. Anyway, once your theory becomes established based on all the data that's available, it's established, and then until later observations discount that theory, you have basically something that is a theory based on observed changes and predictable changes. So let's look at properties of matter. Matter is anything that occupies space and has mass. Matter is made of atoms, and each different type of atom represents a different element. So pull open a periodic table, and you'll look at an element is based on the number of protons in the nucleus. And so it goes from 1 to some very large number, but 1 to in the 90s, 1 to 92, 93, somewhere in there. Hydrogen to the isotopes that degrade through nuclear processes. Anyway, so the periodic table is based on the number of protons in the nucleus, and each element has a unique number of protons in the nucleus, and the number of protons in the nucleus defines the element. For instance, carbon has 6 protons in its nucleus. Whether that carbon atom is on this planet or elsewhere thousands and millions of light years away in the cosmos. If it has 6 protons in the nucleus, it's carbon. And so the beauty of the periodic table is it identifies elements according to their nuclear construct of protons. A substance is a form of matter that has a definite composition and distinct properties. Okay? And so in a chemical sense, the term substance should only be used for elements and compounds. And compounds combinations of atoms to make a molecule or a salt. Of the 118 elements or thereabouts on the periodic table, there are 90 elements that occur in nature, on this planet anyway, and probably most other habitable planets that occur in appreciable amounts. There are 80 elements that have at least one stable isotope. Carbon, for instance, exists 99% as the C12 isotope. But there's a very small percentage of that, 1% or less, that is C13 and C14, meaning that it has additional neutrons in the nucleus. The other 38 elements exist only as radioactive isotopes. Several of these isotopes, when formed, instantly decay to form different elements. And so the definition of chemistry is the exchange of electrons between atoms and molecules. This is all about nuclear chemistry, which is not chemistry, it's really physics. Talking about nuclear decay. It used to be believed that the first 92 elements of the periodic table, hydrogen is 1, 92 is uranium, that all these occur naturally. At first they thought, based on the predictability of the periodic chart, that technetium was not available naturally, but later it was found to be. But it was made by physicists in the laboratory before it was actually discovered in nature. And promethium also. Don't worry about that, but just know that the big picture is what? The periodic table gives us a guided approach to how we can predict different elements and their behavior based on the periodic table. Classifications of matter. Matter is made of atoms, of course, and atoms are three-dimensional entities. They occupy both space and mass, and that is an atom. And as said, as each of the 118 has different atomic number based on the number of protons in the nucleus. Compounds, here we get into our definition. Compounds are comprised of 2 or more elements. Look at that. 2 or more elements. Now, molecular hydrogen, H2, is a molecule, but is it a compound? No, it only has 1 element in the molecule. Water, if you look at water, it has 2 hydrogens and 1 oxygen, and so it is a compound by definition because it has 2 or more elements in the molecular structure. So compounds, so molecular hydrogen, nitrogen, oxygen, they are in their atomic state. They are molecules, but they are not elements. So molecules are the smallest units of compounds. Both hydrogen and water are molecules, but only one is a compound. Water would be the compound. Here are some space filling. You look at that big red, the big red things in the middle. Those are supposed to be oxygen. The space filling is basically the electron cloud associated with that atom. Hydrogen and hydrogen in water. So here's a hydrogen. Here's a hydrogen. Here's the oxygen in molecular water. These 2 electrons here. Every bond has 2 electrons, and so there's 2 electrons shared between these nuclei. And so hydrogen peroxide, peroxide means that oxygen is attached to itself, plus it has, in this case, another hydrogen on one side and hydrogen on the other side. But anyway, that shows the atom-to-atom connectivity. So the molecular structures show you the atom-to-atom connectivity for molecules. So it tells you that oxygen has 2 hydrogens attached to it. That H2O is not 2 hydrogens attached to each other plus an oxygen. No, H2O is this assembly. If you look at this big glob over here, these are macromolecular molecules. Each of these little rivets and shaded areas represent amino acids in a protein, for instance. And this is the gamma globulin for in biological systems. You can see they make very complex structures. Now, going to separation, we can separate materials based on their homogeneity or heterogeneity. Three of the most commonly methods used for physical separation are filtration, distillation, and chromatography, and we'll talk more about chromatography. But filtration is if you have a solid and a liquid combination, it'd be a heterogeneous mixture. You can just put a filter paper in a funnel, pour the mixture into the funnel, and the liquid will go through, and then the mass, the solid, will be trapped by the filter. Let's say you have a homogeneous mixture of two or more liquids. If they have different boiling points, then compound A will boil at a lower temperature than compound B, and compound A will come off first, leaving compound B behind until all of compound A is distilled. And so that is a physical separation of a homogeneous mixture of liquids. Also, we have chromatography, and this little black dot right down here represents an ink dot, and it is posted on a on a piece of paper or a silica gel or something, to where and the solvent is also a part of it, and so you have this solid structure, you have the sample here, and then you have your solvent. In this case, let's say it's water. Anyway, you've seen in your own experience where if you drop maybe a cup of coffee or a drop or two or a spill of coffee on paper, you come back and look at it later and there's some rings around that cup. Well, that's chromatography. And so compounds that are homogeneously mixed can be separated, physically separated, by chromatographic methods. And you can see this little black dot here actually has purple compound, green and looks like navy blue compound, yellow maybe, and also some blue. And so those different colors all represent different compounds. And so chromatography is one method that we use to separate homogeneous mixtures of organic substances generally. So every course has definitions, and so this course is no different. So let's get into the belly of the definitions. A substance has constant composition and properties throughout. Substances can be either elements or compounds. Compounds would be like molecules or ionic associations. A compound is a substance formed when two or more chemical elements are chemically bonded together. That means they're sharing electrons. Chemistry is defined as the sharing of electrons between atoms and molecules. And so a compound would be observed when two or more chemical elements are bonded to each other. Compounds can be decomposed chemically and physically into their constituent elements. And so if you have a compound, you can water would be a compound, for instance, and you can decompose water to its essential elements of hydrogen and oxygen. Looking at mixtures, mixtures contain two or more substances that are not chemically combined, but they just coexist. And so, like you and your roommate, once you become roommates, you still maintain your identity, even though you're in the same container, the room. Mixtures are the same thing for molecules. It contains two or more substances that are not chemically bonded or combined. Mixtures can be homogeneous, where there is no phase boundaries, or they can be heterogeneous, where there are phase boundaries. And the phase boundary is a visible difference between solid and liquid, or liquid and gas, or solid and gas, so on and so forth. So mixtures are unlike chemical compounds because the substances are heterogeneous mixture. And a heterogeneous mixture can be separated physically by using filtration and distillation, so on and so forth. Mixtures have variable compositions, while compounds have a fixed composition, a definite formula. Let's take, for example, hydrogen peroxide, which is H2O2, and water, which is H2O. If I pour those together in a beaker, I have a mixture of two compounds, one of them being water and one of them being hydrogen peroxide. And so they have that mixture. Each molecule has a fixed, definite formula and connectivity of the atoms. So when mixed, individual substances keep their properties in a mixture. Well, if they form a compound, then they change molecular identity, and when they form a compound, their molecular identity is completely changed, and so will their physical and chemical properties change when molecules react to form products. A homogeneous mixture is uniform throughout and contains no visible phase boundaries. Homogeneous vapors, we can have homogeneous mixtures in the gas phase, the liquid phase, and the solid phase. Looking at the gas phase, we'll talk about that as a vapor phase. Air is a mixture of nitrogen, mostly nitrogen, 78%. Oxygen's a little bit more than 21%. Then we have some molecules that exist in tiny traces like carbon dioxide, neon, and other traces of argon, some of the naturally occurring ideal gases. Homogeneous liquid phase would be mixtures of water and various salts. If you took a teaspoon of salt, table salt, and you put it in a glass of pure water and stir it, what happens to the salt? Well, it goes into solution. And so you don't see the solid sodium chloride. The ions have been separated by the water molecules from each other, and so that there are sodium ions and chloride ions suspended in the water matrix. But that, because there's no visible phase boundaries, because sodium chloride is soluble in water, then there's no phase boundaries. If you take something that's insoluble in water, there will be a phase boundary. It'll be heterogeneous. If you look for, maybe as an example, crude oil, when all that oil coming out of the ground is a mixture of organic compounds, mainly hydrocarbons. And so we have very low molecular weight hydrocarbons, say C4, 4 to 5 hydrocarbons, 5 hydrocarbons to 8 hydrocarbons, mixtures like gasoline. But then you get into larger numbers of carbons, which make oils, and then so on and so forth. And so petroleum products are a mixture of hydrocarbons. Ink is another example, as we just illustrated, as a mixture of color bodies. And it's a homogeneous mixture of both of those, or many, if you would, color bodies. Homogeneous in solid phase could be gunpowder. An example would be potassium nitrate, sulfur, and carbon, discovered thousands of years ago in China and later on in Europe, I think. But in any event, gunpowder is a solid heterogeneous mixture. Heterogeneous mixtures contain phase boundaries. Most often they do. They may or may not be uniform throughout. Let's look at ice, a glass of ice water. Okay, if you have ice in water and you look at that, is that homogeneous or heterogeneous? Well, it's heterogeneous because you have a solid phase and a liquid phase. It turns out to be the same molecule, H2O, but what makes it heterogeneous? It's at the interface of the ice compound. So it's the solid-liquid interface at the ice surface that makes it heterogeneous. Fog is a mixture of water and air. Water, of course, you had H2O, and the vapor would be the carrier, it'd be the solute. Here's the basically solvent, not really, but anyway. Um, the phase boundaries at the interface of the suspended water droplets in the liquid and the surrounding vapor. And so it would be an example of another heterogeneous mixture. A carbonated beverage, let's look at that. Let's say you go to the store and you buy a 2-liter bottle of Sprite or 7-Up. It's clear, colorless, and there's no observable phase boundaries. You buy the 2-liter Coke or excuse me, Sprite or whatever, and then as soon as you crack the lid on that thing, you're changing the pressure, because the pressure inside the bottle is greater than the pressure outside the bottle where you are. And so the beverage is carbonated with CO2 is the molecule, and that's what makes it a carbonated beverage, is CO2. And as soon as you crack the lid, it goes from a homogeneous solution to a heterogeneous solution. And where is it a heterogeneous mixture? And so where is the phase boundary? It would be in the bubble between the liquid and the vapor phase. Classification of matter, we can look at a schematic here. Ask the question of any given sample of matter. And so we have any given sample of matter, can it be separated by a physical process? If the answer is no, then it's a substance, okay? And we ask the question then, if it cannot be separated by a physical process, can it be decomposed by a chemical process? If the answer is yes, it's a compound, because it's two or more elements are involved. If the answer is no, then it's an element. And so a substance can be both an element and a compound. Going back to ask the question, can it be separated by a physical process? If the answer is yes, then it's a mixture. Okay. We can separate physical processes through filtration, so on and so forth, chromatography. Is it uniform throughout? If it's not uniform throughout, it has phase boundaries. If it's uniform throughout, it has no phase boundaries, it's homogeneous. And if it has phase boundaries, then it's heterogeneous, not uniform throughout, like fog or something like that. All right. Well, here you have something obviously occurring here on the left. That's a permanganate solid decomposing to it's an oxidation reduction reaction. So what's taking place here? Is it a chemical change or a physical change? What do you think? Well, there's obviously a reaction going on right here. So it's a chemical change, it's decomposition of ammonium dichromate to a more stable molecule exhibiting a big exotherm. Let's look at water, the various phases of water. Here we have water in the solid phase, we have water in the vapor phase, and we have water in the liquid phase. All three phases simultaneously coexisting. Now, water is unique in a certain regard in that it's as a solid, its molecules form a highly ordered structure where there's a lot of empty space between the molecules. And we'll talk about why that is. That's hydrogen bonding between neighboring molecules. Anyway, there's a lot of empty space between molecules in the solid matrix. And so because of that, ice is less dense than liquid water. Because it's less dense, it floats. Liquid water, of course, has molecules that are moving randomly throughout the matrix, and so they have a freedom of movement. When you go to the gas, from a liquid to a gas phase, the water molecules become much further apart and are far less interactive with each other. And so solids, molecules are very close to each other. Liquids, the molecules are much closer to each other. And in the vapor phase, the molecules are much further apart. Let's look at measurement of matter. Most of the world uses the International System of Units, or the metric system. I lived in Europe for 5 years, and it was maddening when I came back to the United States. The United States has It's its own stupid, incoherent system called the imperial system, based on the old British imperial system of inches and pounds. The Brits, by the way, are now metric, and so we're, as a nation, we're one of the only, I think we're the only nation that uses the imperial system. The rest of the world is on the metric system. We have SI units. They're used in conjunction with the metric system. And the metric system is a collection of fundamental units not based on any other units. And I'll elaborate on that. So the metric system uses meters for distance, kilograms for weight, and time is measured in terms of seconds. Electricity is measured in amps. Temperature is measured in either Celsius or Kelvin. Celsius is a more convenient method of measuring temperature of materials, and that's what we use. But we use Kelvin when we're talking about temperature as related to gases. Also, we talk about moles in chemistry. You might remember that. 6.022 times 10 to the 23 items that are identical makes a mole. And the candela or candela, depends on where you're from, luminosity, the intensity of the light, which we will not use in this course. Okay, also in chemistry, we will use the metric system in conjunction with the SI system. So that is a challenge for you to go, because you're living in the imperial world left to us by the damn British, and we are now in science anyway, chemistry, physics, so on and so forth, we're using the metric system. So the International System of Units, abbreviated SI, which comes from the Système International, the French version of the name. So, you know, modifiers before and after, you know, romantic languages, something like that. Anyway, the SI system is the Système International, and it's a scientific method of expressing magnitudes or quantities of matter in terms of time, distance, volume, weight, so on and so forth. So the reference for any SI designation is always related to the unity numeric 1. So is it greater than 1 or less than 1? And that's unity. 1 would be unity. The SI unit prefix often relate to 1 in orders of magnitude, so that which is greater than 1 has a positive exponential. Say 1 times 10 is 10, 10 times 10 is 100, and so that would be you know, an exponential of 2. So anyway, the SI prefixes use exponentials. If it's greater than 1, it's a positive exponential. If it's less than 1, it's a negative exponential. The unit measurement of matter, we'll be using the SI-based units and symbols throughout the course, and you're responsible for them. This table 1.1 in your textbook, the unit for length is meters with a lowercase m. The unit for mass is kilograms, not grams, but kilograms, which is kg. We don't use kilograms in the lab very often, but we certainly use it in industry. But in the laboratory, we'll use grams rather than kilograms. Time is measured in seconds, which is S. Temperature is measured in Kelvin or Celsius. If it's gases, it's Kelvin. If it's liquids or solids, typically we'll use Celsius. The amount of substance, we'll talk about moles, and we won't talk much about amps or candelas in this course. And so the official spelling of meter is M-E-T-R-E. M-E-T-R-E. But the American spelling is as you see it here. The mole, we're going to introduce that in the second chapter. The current, we'll talk about that in terms of the Appendix B in Chapter 20. And then finally, luminous intensity of light will not be discussed in this course. So here's an exhaustive table of SI prefixes. One thing I want to point out to you, and if you're not already familiar with this, is everything is relative to 1. And that can be much greater than 1 or much less than 1. But everything is relative to 1. And so the things that the quantities above 1 that we typically talk about in chemistry is kilogram or kilo, 10 to the third, mega, 10 to the sixth, giga, 10 to the ninth, and tera, 10 to the 12th. That's, okay, so we have 1,000, million, billion, and trillion, if that's the way you want to look at it. So we can also go in the other direction, below 1. Typically in chemistry, we don't use decimeter a lot. We don't use the deci prefix, 10 to the minus 1. Centa we use quite a bit. Milli we use quite a bit. Micro, nano, and very occasionally pico. So those are 10 to the minus 2, 3, 6, 9, and 12. If I were you, I would know those and have those under your command. It's going to be very useful for you, and we're going to be using it for the remainder of the year. So again, just a real quick recap, kilo, mega, giga, and tera we'll use a lot of, and centi, milli, micro, nano, and pico a little bit. Well, let's talk about mass. Mass is anything that occupies space. And mass is the quantity of matter in which an object is measured by its weight. So the quantity of matter as measured by its weight. And of course that has a great deal to do with the gravitational force of constant. Weight is the force of gravity on an object, and all objects have mass. And so we can say the size standard for mass is 1 kilogram. It is not gram, it's 1 kilogram, but a kilogram quantity is not a terribly practical way of doing chemistry in a chemistry laboratory. Kilogram certainly is when you're in a pilot plant in a chemical operation, or even tons are sometimes used. But in a laboratory, we're going to use a gram, which is 10 to the minus 3 kilograms. And so where we have metric system throughout chemistry and throughout science, we also have this thing called the imperial system. Okay, and anytime you have an equality between metric and imperial, you want to write that down, and you need to know that 1 kilogram is equal to 2.2 pounds. The reason you need to know that is because we're going to be doing a lot of unit conversions and having these at the ready. So when we start doing dimensional analysis and unit conversions, you have them at hand. Also, pounds are way too big to worry about. Kilograms are way too big. So just know the conversion. And so for practical reasons, again, we'll use grams, which is 10 to the minus 3 kilograms for measuring mass in most applications in chemistry, rather than the larger quantities of kilograms. And we do not use imperial system. So looking at mass, we'll define mass as m, and we can say that weight is proportional to. We'll use this alpha term quite a bit. That's the Greek alpha. It means proportional in math and in chemistry in this course. And so weight is proportional to the mass. And anytime we have a proportionality, if we're going to make an equality of it, we have to invoke a constant. And so weight then becomes equal to g, the gravitational constant, times the mass. Okay? And so you go from a proportionality to an equality, you have to invoke a constant. And so the gravitational constant, of course, it is what it is. It is note also that again, I'll reiterate, the alpha symbol means proportional. And when you go from proportionality to an equality, you must invoke a constant. Temperature scales. Now, we use in everyday life Fahrenheit. In chemistry, we use Celsius and Kelvin. And so you should be you should have a really good sense of how to convert that, or know how to convert them. But you should have a good sense that um, how to interconvert all of them. We'll use Kelvin in gases. We're going to use Celsius most of the time, and you need to develop an appreciation for the Fahrenheit-Celsius relationship. The Celsius scale, the really important part about the Celsius scale is that it can be converted to kelvins by adding 273. Okay, kelvins is not a temperature, it's an absolute number. But let's go back and look at the Celsius scale for a minute. What's the planet covered with? It's covered with water. And so if we measure the temperature, if we just identify a temperature on a temperature scale where water freezes, we'll call that 0. And then we'll take it up to the boil where water boils, and we'll call that 100. So we go from 0 to 100. That's pretty clever. And just divide it into 100 equal increments, and you have your Celsius scale. The Fahrenheit scale came over from the Brits and other Europeans at the time, where they were using Fahrenheit, and the Fahrenheit scale is 32 degrees for freezing and 212 for boiling. The only thing you need to know about Fahrenheit is how to interconvert Fahrenheit to Celsius, but you won't be doing that very much at all. Just get used to Celsius. Room temperature, a really nice room temperature, a little bit warm perhaps for some of us, 25 degrees. 37 degrees is your body temperature, 98.6 in the Fahrenheit. So there it is. And so we'll look at some conversions. 273K equals 0C, which is freezing. And so on the freezing scale, on the Kelvin scale, freezing is at 273K. And that the boil on the Kelvin scale is 373K. You can convert Fahrenheit to Celsius by taking the Fahrenheit number and multiplying it times 1.8, and then times the Celsius and adding 32. So the Fahrenheit temperature is equal to the Celsius scale times 1.8 plus 32. So again, what's the world covered with? Water. And so where it freezes, we'll call that 0, and we'll call 100 to boil. In chemistry, of course, we use the metric scale, so Celsius for gases, but we also use most of our calculations for gases are in Kelvin. Let's look at volume. Okay. Well, it turns out that water defines not only defines dimensions or volume, it also defines dimensions. Where water boiled at 0C and then boiled at 100C and then froze at 0C, then water is used yet again to identify relationship between volume and mass through density, so on and so forth. So if you take a meter, which is represented in the 3 axes, X, Y, and Z axis, and you take that meter and you chop it down into 10 equal parts, then that would be a centimeter. Each of these equal parts would be a centimeter. And it turns out that 1 cubic centimeter is equal to 1 milliliter. Write that down in your notes. You're going to need that and use that all the time. We use cubic centimeters for volume of solids. We use milliliters for volume of liquids. So for a cube of 10 centimeters along at each axis, then 10 centimeters times 10 centimeters times 10 centimeters is 1,000 cubic centimeters, which is also equal to 1,000 milliliters, which is equal to 1 liter. And so the measurements are in 3 dimensions, so don't forget you're going to have a cubed exponential. All right, so note also, very important conversion, 1 milliliter equals 1 cubic centimeter. Again, we use centimeters cubed when we're talking about volumes of solids, and we use milliliters when we talk about volumes of liquids. So where 1,000 cubic centimeters is equal to 1,000 milliliters, well, milli means 1/1000th, so 1,000 milliliters equals 1 liter. And so 1 liter equals 1,000 cubic centimeters. So looking at volume, again, the units for solids are in cubic centimeters, as I said, and the units for liquids is in milliliters. And there's just a representation that I snagged off of an earlier edition of the same book. It shows you relative, it's just a graphic showing you imperial versus metric. This is the metric centimeter here, here's inches. 2.54 centimeters equals 1 inch. A kilogram, you can see, weighs a whole lot, or has a whole lot more mass than does a pound of the same material. This is a imperial quart. The U.S. quart is what you see in the grocery store. There's a liter of soda. That liter of soda is also represented in this volumetric flask, but you'll get used to interconverting and get a sense of relative quantities and measurements and lengths, so on and so forth, in converting imperial into metric back and forth. So let's look at units. You live and die in this course by units. The SI units for length are the meter. So meter is the SI unit. Kilogram, and that's for length. Mass is kilogram, but we don't use kilograms in the lab. We're going to use grams. The SI unit that we use for time is seconds. The SI unit that we use for temperature is Kelvin. Remember, that's not a degree, that's just an absolute number. And the SI unit that we use for numbers of anything is called the mole. And the mole is equal to 6.022 times 10 to the 23rd articles, items, whatever, per mole of that thing. And so let's say you had a mole of shoes. Well, how many shoes would you have? You would have 6.022 times 10 to the 23rd shoes. Well, that's a lot of shoes. We use these. This number is very, very big because atoms and molecules are so small we can't see them. But we have to have some unity in the way that we interconvert mass and numbers. And numbers come out to be pretty important in chemistry because it leads us basically to stoichiometry when we start talking about stoichiometric coefficients, the mole. Non-SI units typically used in chemistry. Length, we speak of length in terms of angstroms at the atomic scale. For volume, we often use milliliters and not the liters. And for energy, we're always going to use joules. We'll do some joule energy calculations, but a calorie, by the way, it's capital C, calorie, is different in Europe than it is over here. We typically abbreviate it as CAL, and 1 calorie is equal to 4.184 joules. So you might want to write that down. We deal with atmospheres and millimeters of mercury. In Commander Meisenheimer's class, you might have to deal with kilopascals. For pressure in atmospheric pressure would be 1.064 times 10 to the 2, or 106.4 kilopascals for equal 1 atmosphere. But we're going to use atmosphere. Your book likes to use bar, which is almost the same as 1 atmosphere, and I won't get picky on that. But realize when you're doing mastering chemistry, they may be using bar rather than atmospheres when you're doing your calculations for gas pressures. Also, 760 millimeters of mercury, we'll go through how that is derived. Derived units, again, the energy is the only one I really want you to know is the joule, okay? And the joule is equal to kilograms per square meter per kilograms per meter squared, kilograms meter squared, per second squared. But don't get lost in that we'll talk more about joules in terms of energy later on in the course when we talk about thermodynamics. So there's two types of properties that you must know. There's an intensive property. An intensive property. That's a property where it does not depend on the size of the system that you're talking about or the material. Whether you're talking about a cup full or a tanker full, an intensive property like density does not depend on the size of the sample. If you take the density of water as equal to 1 gram per milliliter, or if it was a piece of ice, it'd be 1 gram per cubic centimeter, very closely anyway. That would be an intensive property, like density doesn't change over time or based on how much you have. And for a mnemonic, if you want to think of intensive, just think of independent. And so whatever property you're talking about, if it's independent of the amount, it's an intensive property. Extensive is directly proportional to the amount of material present. Okay, and that would be like heat, things. Density is mass per unit volume, and we typically deal in mass, not in kilograms, but in our derived units of grams. And the volume is going to be a function of the state of the material that we're looking at. It can be grams per cubic centimeter over here for a solid, or it can be grams per milliliter for a liquid. But density, and by the way, grams is what? Is that intensive or extensive? That's an extensive property. Milliliters is an extensive property, measurement, so on and so forth. So we have the combination of two extensive properties gives us an intensive property called density. Okay, and just doing the inner conversions with the arithmetic, you can see how they're derived there. So density is grams per mil for liquids, and density is grams per cubic centimeter for solids. So write those down in your notes. Make sure you're walking around with it. Mass and volume are extensive properties, as I said, and dependent on the amount, but together they make an intensive property in density. The density of water, of pure water, purified water, nothing in it, zero dissolved solids, no electrolytes, nothing. Pure water is 1 gram per milliliter. Wow. Okay, and so now we can have gram per mil, and also what? Gram per cubic centimeter if it's a solid. Okay, and so whether it's a cup full or 25,000 liters of fresh water, it's still 1 gram per mil would be the density of water. Okay, so let's do some unit conversions between metric and imperial system, illustrated through a problem. So what is the gram, what is the mass in grams, metric, of a cube of osmium that is 1.25 inches on each side? So 1.25 in each of the X, Y, Z axes. And we say that the density of osmium is 22.48 grams per cubic centimeter. Okay, well, we're given, let's see, we're given imperial and we're given metric. So we're going to have to do a unit conversion. So our density of a solid is is grams per cubic centimeter. Then we have given to us 1.25 inches. We'll have to cube that, okay, because we want volume. And so where density relates volume to mass, density relates volume to mass using the density function. And so note, and this is very important, any equality that you have, it always results in two true statements, two ratios, arithmetic ratios. Like 12 equals a dozen, well, that you could say 12 per dozen or 1 dozen per 12 items, whatever they are. It's just two ratios with an equality. And so know this well. 2.54 centimeters equals 1 inch. So here's our imperial system. here's our metric system, and here's the way that we can convert. That's the only thing you need. There's the way that we can convert imperial to metric and metric to imperial. And so from this equality, I can write two true statements. There's 1 inch per 2.54 centimeters, or we could say that there's 2.54 centimeters per 1 inch. So let's see where we go next. So here's the setup. We were given 1.25 inches per side, and we want cube. We need to know grams of osmium. And so because we have a length of each side, we want to know the volume. We're going to have to cubic. And so we know that 2.54 centimeters is per inch. And then our inches will cancel out, and we'll cube it. And so what doesn't cancel out is our cubic centimeters. And then when you multiply that times the density of 22.48 grams of osmium per cubic centimeter, then your cubic centimeters will cancel out, and you will have the mass. And so you got to convert from inches to centimeters right here. And this converts centimeters to cubic centimeters, which can then be canceled out in the density function. Okay, and so the mass to answer this question is 719 grams of osmium. You should be able to do this and recognize that anytime you have an imperial measurement or mass, an imperial unit, you need to be able to convert that to the metric equivalent. So uncertainties in scientific measurement. There's a lot of uncertainties, and sometimes it's important to know from which that certain uncertainty lies. No matter how careful you are, there's usually going to be error in a measurement of some sort. Error is not necessarily a mistake. It's part of the measuring process. And in science, measurement error is called experimental error or observational error, right? And so there's two broad classes of observational errors. There's systematic errors and there's random errors. And we'll talk about each of those. So systematic errors is consistent. It's repeatable error associated with a faulty piece of equipment or a flawed experimental design. That's systematic error. Let's say a thermometer regularly reads 2 degrees lower than what it really should. So let's say water boils at 100 degrees C. Let's say our thermometer measures 98 C when it's put it in boiling water. That would be a systematic error. Okay. Systematic error has the same value or proportion for every measurement, and it's highly repeatable. All right. As long as you know you have systematic error, and it will be repeatable, then you need to remediate that systematic error in your measurement. They usually are caused by the measuring instruments that are either not correctly calibrated. Everything that you use must be calibrated. Or there's something wrong with the instrument, or finally its data handling system is defective. So maybe an algorithm is incorrect in calculating a wave function or something like that. That would be an evidence of a systematic error that will be the same every time you do a measurement. And so, or the instrument is used incorrectly. Sometimes if you have these highly sophisticated instruments in the lab, if you're not using it incorrectly, then you'll have systematic error built in. And I think that's also probably a close cousin to random error. Depends if it's in the if the problem is in the cockpit or in the plane. All right, random errors are in experimental measurements that are caused by unknown or unpredictable changes in the experiment. That could be experimental conditions like the temperature of the room, or it could be the atmospheric pressure of the day. It could be a lot of different things. Random errors are unavoidable, but cluster around a true value. And so a random error varies unpredictably from one measurement to another, while systematic error has the same value or proportion to every measurement. And so the variability of a random error is unpredictable. Let's say you and your buddy measured the length of a rod using a centimeter scale that was fractioned down into millimeters of measurement, chances are your measurement is going to be slightly different than your buddy, and that would be an example of random error. These changes may also result in experimental or environmental conditions, as I had mentioned earlier. So 2 or more people making the same measurement with the same instrument under identical conditions but arrive at different values is an example of random error. And you'll see lots of that in your experiments. So now we're going to consider the differences between precision and accuracy. Precision is the reproducibility of a measurement, and accuracy is how close the measurement is to the true value or to the real value. And so reproducibility and precision, accuracy, proximity to the true value. We have 2 scales. The one on the left reads to 1/10 of a gram, or 10 to the minus 1 grams if you prefer. And the one on the right, the measurement goes out to 10 to the minus 4. All right, so looking at the scale to the right, what is the most precise number that you can quote? The absolutely most precise number you can quote. Well, the greatest variability that you're going to have with this instrument is going to be in that last digit. And so the numbers that you have absolute confidence in, barring any systematic errors, would be you could report that this sample weighs 10.497 grams. You can say that without equivocation if there's no systematic error. And it's that last digit that is probably where you're going to find most of your systematic error. And so you could report then 10.497 grams would be your most accurate, most precise, I should say. And where does the variability lie in scale number 2? Well, it lies at that 8, that last 8 identified in the red there. And so that is where your greatest variability lies. The number that you can say that is true is 10.497, probably 0.4978 if there's no variability in the instrument itself. All right, scientific notation. All right, so as we're going to talk about later on, we're going to have a reference point for something on the planet, which is carbon. Carbon might find it interesting that carbon is less than 1% of the total mass of the entire planet, but it is a large abundance, much greater than 1% certainly, on the surface of the Earth. But in any event, if you look at the number of carbon-12 atoms, meaning 12 protons and 12 neutrons, and exactly 12 grams of carbon-12 carbon, then the number of atoms would be 6.02 or 602. So we're talking this big, huge number. Well, we don't want to write all those zeros down. Nobody does. And so we're going to invoke scientific notation. And so this number is much greater than 1. And so that'll be a positive exponential. And so we'll take our reading. We'll go from here all the way back over to here, and we'll report 1 unit with a decimal point, followed by some other numbers beyond the decimal point, times an exponential. And the exponential is a function of how many zeros that or how many places that you moved to the left on that number. And so this number would be reported as 6.022 times 10 to the 23, meaning that there's 23 spaces between here and here, or 23 digit zeros. The mass of a single carbon atom. Now we're getting pretty small here. Okay, so what's the exponential going to look like here? It's going to be negative. So we went from right to left, it was positive. We go from left to right, it's negative. And so this would be 1.99 times 10 to the minus 23 grams per, and that's how much 1 atom of carbon weighs for carbon-12. And so we have the integer n times some exponential, or times 10 to some exponential. That exponential can be a positive number or it can be a negative number. Okay, so that when and n is always between 1 and 10. Actually, it'd be between 1 and 9, really, but anyway, 1 and 10. And then n is a positive integer if the number is larger than 1, and it's a negative integer in the exponential if it's smaller than 1. So what would 568.762, how would you represent that through scientific notation? Well, we're going to take this, our number, and we're going to take this and move it over to a single digit. And how many digits did we move over to the left? 2. And so n, that's greater than 0, okay? And so we're going to say then that 568.762 is really 5.68762 times 10 to the 2, because we moved to the left 2 decimal places from here to here. All right, and so 10 to the 2 indicates something positive greater than 1. How about this number? What would that number be in scientific notation? How many places are you going to have to move over? 1, 2, 3, 4, 5, 6 until you get to that 7, the first digit. And so you would move it to the right, and n is going to be less than 0 or less than 1, certainly. And so that would be expressed as 7.72 times 10 to the minus 6th. Why? Because it's much less than 1, and you had to move over 6 digits to get a positive or to get a whole number or a fraction of a whole number. So in addition and subtraction, when scientific notation is at hand, when you're adding or subtracting numbers with exponentials, you write each quantity with the same exponent, meaning that you're going to have to convert. And so then you combine addition or subtraction. You combine the integers in front of the exponentials, or in front of the 10 exponential. And so you combine n1 and n2. It could be either adding or subtracting. And the exponent remains the same once you've converted, so made everything exponentially identical. And so how would we do that with 4.31 times 10 to the 4th plus 3.9 times 10 to the 3? Well, we're going to have to either report this number as 10 to the 4th or 10 to the 3. And so if we take 10 to the 4th as our reference point, because that's the larger one, it's still 4.31 times 10 to the 4th, but now we've moved this one over by 1 decimal place, and that makes it 0.39. So it went from 3.9 to 0.39, and it went from 3.9 times 10 to the 3rd down to 0.39 times 10 to the 4th. So now our exponentials are the same, and because they're the same, then we can add these numbers together. And it turns out to be 4.7 times 10 to the 4th. So in adding and subtracting numbers with scientific notation, you take the integer in front of the 10 exponential, and you add or subtract those. But first, you must make all exponentials identical. So 10 to the 4th is not the same as 10 to the 3. We're going to convert 10 to the 3 to 10 to the 4th by moving the decimal place over to the left. In multiplication for scientific notation, we multiply the integers n1 and n2, and we add the exponents. And so in multiplication, we're going to add the exponentials of n1 and n2. And so let's multiply 4 times 10 to the minus 5th. We'll take that, which is what, 0.000004. And we're going to add that to 7 times 10 to the 3rd, so that's 7,000. Okay, and so what are we going to have to do first? Well, we're going to have to add the numbers of 4 and 7, as indicated down here, times 10 to the, well, we're going to take our exponentials, and we're going to either add or subtract them. In this case, it's a -5, which is our exponential, and then we'll add 3 to that, And so that'd be minus, 10 to the minus 2. And so we'll add these two numbers together. We'll multiply them, 4 times 7 is 28 times 10 to the minus 2. But we have to, in scientific notation, we have to report it to a 1 decimal point. And so it'd be 10 to the minus 1. So we'd have to move it over from 28 to 2.8. And in doing so, we will reduce the exponential by a factor of -1. In division, for exponentials, we always divide the integers, and then we subtract the exponentials, n1 and n2. So we're going to, for example, divide 8.5 times 10 to the 4th by 5 times 5.0 times 10 to the minus 9th. And so what are we going to do with our exponentials? We're going to subtract them, and we will divide 8.5 divided by 5. Okay, and so we're going to say 8.5 divided by 5 times 10 to the 4 minus 9. So 4 over here minus 9 over there. Okay, and that's going to give us a 1.7 times 10 to the minus 5th. So once you've divided 8.5 by 5, you're going to get 1.7, and you subtracted the exponentials when you're dividing, and so you subtract the exponential of 4, you subtract the exponential of 9 from the 4, and it gives you 10 to the minus 5th. Significant figures. Don't let your computer or don't let your calculator lie to you. Do not get in the habit of reporting. Just because your calculator can calculate, let's say you've got it set at 10 figures or 9 or 8 figures. If you report 8 figures when there's no possible way you can be that accurate or that precise, then you're really getting, sig figs are getting into your way. So you need to be able to figure out pretty much what figures are significant in mathematical treatment. And so any digit that is not a 0 is significant. Number one, any digit that is not a 0 is significant. So 1.234 has 4 significant figures, 4 non-zero numbers. Zeros between non-zeros are significant. So not only the number is significant that are not 0, but a 0 that is between numbers is also significant. And so 606 is 3 significant figures because a 0 is between 2 non-zero numbers, okay, 6 and 6. So there's 3 sig figs there. Zeros to the left of the first non-zero digit are not significant. Okay, let's look at that. So 0.08 liters has 1 sig fig, because it has zeros to the left of the first non-zero digit are not significant. So there you go. So you have 1 sig fig there. If a number is greater than 1, then all zeros to the right of the decimal point are significant. If the number is greater than 1, that's the caveat. And so 2 is certainly greater than 1, and so 2.0 has 2 sig figs because 2, the value 2, is greater than the absolute value of 1. If a number is less than 1, then only the zeros that end in the middle or on the that are at the end of that number or in the middle of that number are significant. Numbers preceding that first whole number is not significant. Okay, and so how many sig figs can you see here? So these zeros occur before the non-zero 4, and so that would be 3 sig figs because we said that the zeros after the first non-zeros are significant, and so there'd be 3 sig figs there. And so looking at this number here, 0.004004500, let's look at numbers that are significant and numbers that are not. The numbers that are occurring before the first non-zero number 4, these are not significant for cosmetic purposes anyway. And these other two are also not significant because the locant they're there before the first non-zero number. The numbers 4 and 5 are significant. They're all non-zero numbers, so they are significant. These two zeros, because they're between two non-zero numbers, are also significant. And we said that any number that involves zeros to the right, to the end of that number, are significant as well. And so how many sig figs are there? 1, 2, 3, 4, 5, 6, 7. So 7 sig figs. So let's go through some exercises. How many significant figures are in each of the following measurements? 24 milliliters, how many sig figs? 2. 2 significant figures. All right, 3001 grams. Okay, so that's certainly greater than 1. What do you see here? 2 zeros between two non-zero numbers. So are they significant? Yes. So that's 4 significant figures. What about 0.0320? What about, are these zeros, because this number is less than 1, are these zeros significant? No. Is this zero significant? Yes, it is. So there's 3 sig figs there. 6.4 times 10 to the 4th molecules, okay, has 2 sig figs because it's expressed. You don't. If you had written it out as 6,000 or 64,000 molecules, then you'd have all sig figs. But you reported it as 6.4. So the only significant figures in exponential representation are the whole numbers. And we follow the zero rules as well. So there's 2 sig figs there. 560 kilograms, certainly greater than 1. So is that 0 significant? Yep. It's a little bit ambiguous. If it's a measured number, it's significant. If it's a non-measured number, it is not significant. So there's 2 sig figs if you're counting it as kilograms, or 3 sig figs if you're looking at the 0 there. Addition or subtraction using significant figures. The answer cannot have more digits to the right of the decimal point than any of the original numbers. So let's look at adding and subtracting numbers with non-whole numbers. And so we'd have 89.332, and we're going to add 1.1 to that. Okay, that gives us 90.432. But what number has the least significant figures? That one right there. And so there's 1 sig fig after the decimal point, and so you round off to 90.4. Let's take 3.7 and subtract from it 2.9133. And when you do that on your calculator, you're going to get 0.7867. Okay, but how many sig figs do you have? 2 sig figs after the decimal point in the top number, and so your number that you read or report can have no more than 2 sig figs after the decimal point, and so you round off to 0.79 because this 6 is going to round you up to the 9. Multiplication and division using sig figs. The number of the significant figures is a result that is set by the original number that has the smallest number of sig figs. Okay, so you cannot be any more significant than the least significant number. And so we're going to take 4.51 and multiply it on your handy dandy little calculator times 3.6666, 4 sixes after that decimal point. And your calculator is going to give you some ridiculous number like this. But how many sig figs can you honestly report? Which one has the least number of sig figs? So that'd be 4.51. And so there's 3 sig figs there. And so you're going to have to round your answer out to 3 sig figs, which would be 16.5. All right, let's divide 6.8 by 112.04, and we get a number of 0.0606926, Okay, well, how many sig figs, which number has the least number of significant figures? That'd be 6.8. Okay, and so your number, the original number that is the smallest sig figs is 6.88, and so your answer can have no more than 2 significant figures, and so we're going to round to 2 sig figs here, and so we're going to say it's 0.061. Accuracy and precision. So here we are at the pistol range, and you have a so your accuracy and precision. So accuracy is how close the measurement is to the true value, and precision is how close the set of measurements are to each other. All right, and so this is both accurate and precise. And what is the next one on the right? We have a tight grouping up here. Need some sight adjustment on your pistol, but they're all clustered very, very close in value, and so they're very precise, but they're not accurate. Okay, and here's your guy that's been on the pistol range for 1 or 2 times, and he's shooting for the target here, and he or she is getting numbers all over the place, so it's neither precise or accurate. Okay, so we're going to look at dimensional analysis method of solving problems. One thing that we experience in chemistry are multiple types of units, metric to metric, or imperial to metric, or metric to imperial, whatever. But we have a cascade of multiplication and divisions that we have to do in the right way to get the right answer. And this would be using dimensional analysis. Most of you, I'll be straight up with you, are not really good at dimensional analysis. You can get lost in the weeds pretty quickly if you're not very methodical about it. Some of you guys are pretty sharp at this, but most of you aren't. So let's look at it from a stepwise basis and look at the logic. So the first thing you need to determine is which unit conversion factors are needed. Okay, so if you're converting feet to inches, or you're converting inches to milliliters or centimeters, you have to determine which conversion factors are needed. That's where your qualities come in. To carry the units through the calculation so that all your units cancel in both numerator and denominator. And if all the units cancel except the desired units, then the problem is solved correctly. Very important. If all the units cancel, all the units have to cancel, then the problem is solved correctly. If not, you did not solve the problem correctly. Now, one of the problems that most of you have is if I give you a problem on the board or whatever, the first thing you do is you're going to grab that calculator, start punching numbers. Do not do that. Do not, when I give you a problem, do not pick up that calculator until you have set it up on paper where you've canceled your units. Then use that calculator. To a person, 99% of you, if not 100%, if I put a problem up on the board, first thing you do is going to grab that damn calculator and start punching numbers. Well, the calculator is stupid. It's absolutely stupid. And it's going to give you whatever numbers that you give in multiplication and division. And so set it out on paper first. If you have to do it stepwise, do it stepwise. But you cannot fail if you use ratios. And for every quality, you have 2 ratios. Okay, so we're going to go through a very stepwise procedure. So we're going to take a given quantity, and we're going to multiply that given quantity times a conversion factor to give us the desired quantity. Well, that looks pretty simple, right? But actually, this can be a 2-part, 3-part, 4-part, 5-part, 6, 7, 8-part type conversion factors. And that's where you get really screwed up in your dimensional analysis. A 2-dimensional factor is easy enough. Miles per hour versus feet per hour, things like that. Those are easy enough. But when you get into multiple conversion factors, that's where your ratios better be on. You better be on top of your ratios. So let's say we're given unit X, and we're going to divide it by we're going to multiply it by a ratio of desired unit by a given unit. Now, which cancel out? The given units in the denominator cancel out with the given units in the initial scenario. What does that leave behind after you've canceled the given units is the desired unit. Okay, and so canceling out the given units, you're left with the desired unit. All right, easy peasy. Numerator and denominator must cancel out. And so let's do a dimensional analysis problem looking at the following. So how many milliliters are in 1.63 liters? Well, that doesn't look terribly challenging, but let's set it up. What do we know about liters and milliliters? There's an equality. 1 liter equals 1,000 milliliters. And from that equality, what can we do? We can write two ratios. Both of them are true. There's 1,000 milliliters per every 1 liter, or there's 1 liter for every 1,000 milliliters. Both of these statements are true. And you're still within the metric system, by the way. Okay, and so you're using your unit conversions, orders of magnitude, really, from liters to milliliters. And you want to know how many milliliters are in 1.63 liters. So what are you given? 1.63 liters. And which of these two are you going to use to cancel out liters? Well, you're going to use this one and multiply it times this so that your numerator will cancel out the denominator. So let's set it up. You won't use this one. All right, and so there's 1.63 liters given in the problem. And we're going to use the ratio of 1,000 mils per liter. That's right here, 1,000 mils per liter. This way, our liters cancel out in the given unit, in the numerator, and cancel out in the denominator. And what are we left with that we want to know? Milliliters. So that's 1,630 milliliters. How many sig figs are there? 4. All right. So 1.63 liters, and let's use the incorrect one just to show you. If we use this ratio in your stupid little calculator, and you took 1.633 and divided it by 1,000, you would actually have 0.00163, and what would be your units? Liters squared per milliliter. Well, that's stupid. That doesn't make any sense at all. If your units don't make sense, you have screwed it up, and you need to go back, write the ratios out, and take the one that works. Leave the other one behind. Okay, so here we are, canceling out our units not canceling out, excuse me, so it'd be liters squared over milliliter. So you don't want to do that. Use the correct one where liters cancel out in the denominator as seen over here. All right, so what's the speed of air? The speed of sound in air turns out to be 343 meters per second. All right. What is it what is the speed in miles per hour? So what's the speed of sound in miles per hour when we're given it in meters per second? So hour is a measurement of time, as is seconds, and miles is a measurement of what distance, as is meters. And so we're going to have some conversion factors that we're going to need to look at. What do we want our units to be at the end of the multiplication and division? We want miles in the numerator and hours in the denominator. Okay, so what are the conversion units? Meters to miles and seconds to hours. That's what we're going to have to convert. Again, metric distance versus imperial distance. And this is just the clock. All right, so let's set up our 3 equalities that must be considered. 1 mile equals 1,609 meters. All right, that's just a given. You're going to have to know that or have it embedded in the problem. Anyway, 1 mile is 1,609 meters. So that's an equality. What can you do with that equality? Make 2 ratios, okay? And also, we know for the time conversion here, we know that 1 minute is equal to 60 seconds, and that 1 hour is equal to 60 minutes. So we have 3 equalities. Each of them I can write 2 ratios. So how many ratios can I write down? I'm only going to use 3, but I'm going to have to write down 6 ratios. There's 1 mile per 1,609 meters, or there's 1,609 meters per 1 mile. Both of those ratios would be accurate for that equality. There's 1 minute per 60 seconds, or 60 seconds per 1 minute. Those would be your ratios there. And then there's 60 minutes per 1 hour, or 1 hour per 60 minutes. Those would be your 2 ratios there. All right. And so 2 ratios can be correctly written for each quantity. Write them down before doing the problem. Do not pick up that calculator until you've written down all equalities, or all ratios for the equalities. So there's one set of equalities for miles and meters right there. And here's the conversion in seconds and minutes right there. Those are the 2 ratios. And we can write it also for hours. We can write it 1 hour per 60 minutes, or 60 minutes per 1 hour. And in doing so, for each equality, both statements are true. But so you have how many ratios? You have 6 ratios showing there. Okay, but you're going to use 3 of them. What are you given in the problem? 343 meters per second. And you want to convert meters to miles and seconds to hours. Okay, so use the one that allows for calculation. So here we are, same problem. I'm given 343 meters per second. And what I want to cancel, which of these is going to give me meters in the denominator? Well, this one. That would be 1 mile per 1,609 meters. Okay, so now my meters are going to cancel out. I'm left with miles per second. All right, so now I'm going to have to convert, because we want miles in the numerator. So that guy is done. Now we got to work on this one, the seconds. Okay, and so we're going to have to multiply. We're going to have seconds in the numerator. And so where do we have seconds in the numerator? Right here, 60 seconds per minute. And so we're going to multiply that, all right, using the ratio of 60 seconds per minute. And now my seconds are going to cancel out. And what am I left with? Miles per minute. But we don't want that. We want what? Miles per hour. And so over here, we have 2 equalities. There's 1 hour per 60 minutes, or 60 minutes per 1 hour. And what do you want to do? Cancel minutes and leave hours. And so you use the ratio of 60 minutes per 1 hour. Okay. And now let's cancel out units. So what units are left uncanceled? Miles and hours. So go ahead and cancel out units. So we'll have, once you've canceled out units, you have 767 miles per hour. And there's the cancellation of numerator meters to denominator meters. All right, cancellation of denominator seconds to numerator seconds. And we're going to cancel out numerator minutes and denominator minutes. All right, and what are we left with that's not canceled out? Miles per hour. Now guys, this is going to be the pitfall right here, where you're doing multiple conversions. If you don't write them down, you don't write all these ratios down, there's one arithmetic function there, there's another arithmetic function here, another arithmetic function there. There's 3 arithmetic functions that you're going to have to do. And without writing down the units and without taking care to cancel out your units, you have, what, a 1 in 6 chance of getting it correct. So that'll end our overview of Chapter 1. Hope it was edifying for you. Please don't hesitate to come forward and email me with a question at samstevenson@marionmilitary.edu. I'll put in my personal information in the syllabus where you can text me as well. Or also, don't forget, there's Zoom questions and tutors. So you've got the foundation now for finishing mastering chemistry. You should have been keeping up along with mastering as we go along in this lecture for Chapter 1, and be ready for the next.